This is the second video in our reactions in stoichiometry unit. This video is the second part of the lessons on Learning Goal 5.1a on chemical equations. This video will cover success criteria C and D for this learning goal. Speaking of the learning goal, we are still on the Learning Goal 5.1a. I understand how chemical reactions are represented. In this lesson, we will look at the success criterion C. I can explain what it means to balance an equation and why it must be done. And also success criterion D, I can balance chemical equations. I want to start with an example, and eventually we're going to ask this question here: where did the oxygen atom go? I want you to consider the equation for the formation of water that we had from the last video. So we wrote this equation. The reaction might have been stated something like hydrogen and oxygen react to form water. And notice we have H2 and O2 because both hydrogen and oxygen are diatomic. And those two are reacting to form water, which we know the formula is H2O. But if we think about the atoms involved here, and I have some images to help us with this, we'll notice that we're missing an oxygen atom, or at least we seem to be missing an oxygen atom. So for example, we have our hydrogen here, and hydrogen is a 2-atom molecule, thus I have the two blue atoms there to represent hydrogen. And then oxygen is 2 oxygen atoms. I use the red atoms here to represent that. And then if I take a look at what my water molecule would look like, you see the water molecule here with the 2 hydrogens, again those 2 blue atoms, and then the 1 red for the oxygen. You can see very clearly here that we have 1 less oxygen on the right side than we do on the left side, because I had 2 atoms of oxygen here, but now I only have 1. So the question is, what happened to the other oxygen atom? And here's what we need to recognize, that in chemical reactions, the only thing atoms can do, they're either combined, separated, and or rearranged. We don't get to gain any atoms, we don't get to lose any atoms. So in reality, we didn't lose an oxygen atom. So the question is, well, where is it then? Well, as it turns out, we're not really representing our equation entirely truthfully as we have it written here. In other words, what we're saying here is that matter is neither created nor destroyed in any chemical reaction. This is known as the conservation of mass. So in other words, whatever atoms we start with, we also have to end with. So whatever atoms we have on the left side of the equation, we have to have on the right side. Now you can see, as we've written this equation here, that is clearly not the case, because we are missing an oxygen atom, at least the way we're writing it. So as it turns out, whenever we write these equations, we can have more than 1 particle involved. So as we have this equation written here, we just have a single hydrogen molecule, we have a single oxygen molecule, and a single water molecule. But what if we had this instead? What if instead we had 2 hydrogen molecules reacting with the 1 oxygen molecule to give us 2 water molecules? Think about what that would look like. So here are my 2 hydrogen molecules, each with 2 hydrogen atoms, so 4 hydrogen atoms there in total, reacting with the 1 oxygen molecule, so the 2 oxygen atoms in total, and then we would get 2 molecules of water. And notice now, if we look at that, I have 4 hydrogens on each side. I have 4 the blue atoms here, 4 of the blue atoms here, and I have 2 oxygen atoms on each side. 2 of the oxygen atoms here, 2 of the oxygen atoms here. Now we can see that we have not gained or lost any atoms. The only thing that happened was the atoms were either combined, separated, and or rearranged. More specifically, what happened is all these atoms got separated. The hydrogens are no longer bonded to each other, and the oxygens are no longer bonded to each other, and then they recombined, where each of the individual hydrogens is now bonded to 1 of the oxygens that we can see over here. This is an example, as this equation is written here, of what we call a balanced equation. Balanced meaning we have the same number of atoms of all elements on both sides. I have 4 hydrogen atoms on the left, I have 4 hydrogen atoms on the right. I have 2 oxygen atoms on the left. I have 2 oxygen atoms on the right. This is a balanced equation. So, just to review what we just learned from that slide, balanced equations are whenever we have the same number of atoms of each element on both sides, meaning the reactant side, the product side of the equation. Now, one thing to keep in mind when we say the same number of atoms of each element, that does not mean that every single element has to have the exact same number of atoms as every other element. If you think about the last example, we had 4 hydrogen atoms on each side, we had 2 oxygen atoms on each side. That's balanced. It does not mean we have to have 4 of every element or 2 of every element. Just as long as each element has the same number of atoms on both sides compared to the same element on the other. Those numbers that are out front of the equation of each symbol, we call those coefficients, those show how many particles there are of each substance. So when we look at this equation, again the same one from the previous example, I now have a 2 coefficient in front of the H2. That just means I have 2 molecules of H2. And I have a 2 coefficient in front of the water. It means I have 2 molecules of water. If there is no coefficient, like you see here in front of O2, just like in math class, it's understood to be 1. So just because I don't put a 1 there does not mean that there's 0. So just think in math class, if you had the symbol X, that's the same thing as 1x. So when we just see O2 here, it means we have 1 molecule of the O2. So in other words, because these coefficients show us the number of particles, we can see here that 2 molecules of hydrogen and 1 molecule of oxygen will form 2 molecules of water. That's actually what's occurring in this reaction. So before, when we just wrote H2 plus O2 produces H2O, well, that tells us all the substances involved. It does not really tell us how the reaction is actually occurring. This does. Well, I can see very clearly here that I will have 2 molecules of hydrogen combined with the 1 molecule of oxygen to give us the 2 molecules of water. So equations are balanced to show how many particles, meaning atoms and molecules, of each substance are involved in the reaction. This is what accounts for that whole law of conservation of mass. We said that tells us that atoms can't be created nor destroyed, that whatever atoms we start with, we also have to end with. And so this is why we balance equations. All right, so the next question becomes, how in the heck do we do this? How do we look at an equation and balance it? Well, I have several examples here, and through lots of experience, what I will tell you, the best way to get good at this stuff is just to practice it a lot. There is not one single list of steps I can give you as far as do A, B, C, D, E, and then it's going to be balanced, because every equation is different. If I were to try to give you a list of steps, the steps would have to be dozens and dozens long. Now that being said, with these examples, I have several different hints or tricks or tips to show you. These just come from experience. The more you do this, the more comfortable you will get with balancing these equations. So let's just jump right in. So let's say we have this equation here. So we have magnesium reacting with hydrochloric acid or hydrogen chloride, and we're getting magnesium chloride and hydrogen. So there are some basic steps that you will do with pretty much all these equations, and I kind of show you these on this first example. The first thing you want to do is count the number of atoms of each element on both sides of the equation. So when you're first starting to do this, here's what I would do. I would just write the symbols of all the elements that are in the reaction right below the arrow. That way you can separate the equation into the 2 sides, my reactant side, my product side. So this particular equation, we have magnesium, we have hydrogen, we have chlorine. So I'm listing those elements, their symbols there, right below the arrow. I will now count how many of each atom I have of all those elements on either side. So on the left side, I can see I have 1 magnesium atom. It's right here. On the right side, I also have 1 magnesium atom. Remember, this subscript 2, because there are no parentheses, only applies to the chlorine. Okay, remember that 2 does not go with the magnesium. On the left side, I have 1 hydrogen. And on the right side, I have the 2 hydrogens that you can see there. On the left side, I have 1 chlorine. On the right side, I have 2 chlorines. So I've done my count. Now, this process down here that I'm showing is not really part of the balancing. I just really think it helps students as they're learning how to do this for keeping track of where they are with the counts. That way you can keep yourself focused on what needs to be done and what's already balanced. What we're doing here in and of itself is doing nothing for balancing the equation. The only thing that we can do to balance the equation, and this is the next step here, is to change the coefficients that are in front of the symbols and the formulas to balance the equation. Right now in my equation, I'm showing one particle of each of these. One atom of magnesium with one molecule of hydrogen chloride, with one molecule of magnesium chloride, with one molecule of hydrogen. But I can see that my equation isn't balanced doing that because I don't have the same number of atoms on both sides. So notice I have 2 atoms of hydrogen on the right, but I only have 1 on the left. So ask yourself, what can I do to change coefficients to give me 2 atoms of hydrogen on the left? Well, if I had 2 molecules of the HCl, that would give me 2 atoms of hydrogen. So if I had 2 of that whole thing, I would have 2 atoms of hydrogen. So my next hint here is to update the counts with the addition of each coefficient. So now that I put a 2 here, I'm going to go back and I'm going to cross out my 1. I'm going to say, well, I now have 2 hydrogens. But here's the thing. I didn't just change the hydrogen. Because I have 2 of this entire thing, I also now have 2 chlorines. So notice now this equation is balanced. I have 1 atom of magnesium on each side. I have 2 atoms of hydrogen on each side. I have 2 atoms of chlorine on each side. So the equation has been balanced. The thing that we always need to keep in mind, and there is never an exception to this, we cannot change the formulas of the substances in it. So in other words, what I could not do, I couldn't simply go in and put a subscript 2 here next to the Cl to give me 2 chlorine atoms. And the reason why that is, because I do ask you the question here, why not, is the formula for hydrochloric acid or hydrogen chloride is HCl. It's not HCl2. So I can't go in and change the formula to make it balanced. The only thing we can do is change the coefficients. Go from 1 particle to 2 to 5 or however many it takes. That's the only thing we can do to balance the equation. All right, let's look at a lot more examples here. Next example. So here you can see it looks more complex. I have more elements, but actually this one is very straightforward, and you'll see why. When I balance this, notice that we see NO3, that polyatomic ion, on both sides. I see the nitrate ion here. I also see the nitrate ion here. So here the tip is to, whenever possible, balance polyatomic ions as one unit. So notice I'm not writing nitrogen and oxygen separately here. I'm going to balance that entire nitrate ion, NO3, like it's one atom. It'll make it much easier to do. So when I count this, I have 1 copper on the left, and I have just 1 on the right. Okay, remember, this 2 here only goes with what's inside the parentheses. That 2 does not apply to the copper, so it's just 1 atom of copper. I have 1 silver atom on the left, and I have the 1 silver atom on the right, because again, no subscript there. Now here's where we can balance this polyatomic ion as a unit. Instead of saying I have 1 nitrogen and 3 oxygen atoms, I look at this, and in that whole thing, I see there's just 1 nitrate ion. Again, NO3 is 1 ion. I'm going to balance it as such. And on the right, because of the parentheses and the subscript 2 here, I can see we have 2 nitrate ions on the right. So this will make it a lot easier to balance. So now it's just a matter of changing some coefficients. So the first thing I can see here, copper and silver are balanced, at least to start with, but my nitrates are not. I need 2 nitrate ions on the left side. Well, to do that, again, I can't change the formula any. I cannot go through here and put parentheses around the NO3 and put a 2 outside of it. I can't change the formula. But what I can do is have 2 of that entire molecule. So if I have 2 of those silver nitrates, that will give me 2 nitrate ions. But recognize I did not just change the nitrate, I now also have 2 silver atoms as well. Well, now that I have 2 silver atoms on the left, I'm going to need 2 silver atoms here on the right. So I will need a 2 coefficient here in front of the silver, and that will change my count there to 2. So now notice it's balanced. I have 1 copper atom on each side, 2 silver atoms, and 2 nitrate ions. So that's balanced. All right, let's look at another example. So this one's a bit more complex. At first glance, it might not look like so. So notice our elements are carbon, hydrogen, and oxygen. Here my hint is this. Oh, let's get our count here first. So I have 2 carbons on the left. I can see those there. I have just the 1 carbon on the right. Again, remember that 2 only applies to the oxygen, not to the carbon. I have 6 hydrogens on the left, and I have the 2 hydrogens on the right there. I can see that with the subscript 2. I have 2 oxygens on the left, O2. Then on the right, it's a very common mistake for students to either write 2 or to write 1 oxygen, but in reality there are 3. Because notice I have 2 oxygens here in the CO2. I also have the 1 in the water, so there are 3 oxygens in total there. So at first this might look like it's kind of hard. It is a little bit because none of the elements are balanced to start with. And the question might be, well, where do we start? Well, ultimately, it doesn't matter where you start, but there are some ways of doing it that make it easier than others. And here's what you want to keep in mind. You want to save any lone elements for last. Notice oxygen here is by itself. It's not in a compound with any other element. So that's a lone element. I'm going to save that for last. The reason being, if I get the carbons and the hydrogens balanced first, I can then go in and put whatever coefficient I want right here, and all I'm changing is the oxygen. Whereas if I change any of the other coefficients, this one, or this one, I'm not just changing one element. I'm changing hydrogen and oxygen, or carbon and oxygen, or carbon and hydrogen. So I'm going to save the oxygens for last. So to balance the carbons, I can see I have 2 carbons on the left. To give me 2 carbons on the right, I'm going to give myself 2 molecules of the CO2. So that will change my 1 count to a 2. But then I also change the oxygens now. So notice I have 4 oxygens here. 2 times 2 is 4. Plus the 1 here in the water, so that's 5 oxygens. So every time you change a coefficient, update the counts for all the elements that it changes. So now let's balance the hydrogens. I have 6 hydrogens here on the left. So ask yourself, how many water molecules do I need to give me 6 hydrogen atoms on the right? Well, the answer there is 3, because every water molecule has 2 hydrogens, and 3 times 2 is 6. So notice it's not 3 plus 2. Because when I put a 3 here, it means I have 3 of that entire thing. So I have H2O, H2O, H2O. 2 plus 2 plus 2, or 2 times 3, is 6. So that gives me 6 hydrogens. But again, I also change the oxygens. So I have the 4 oxygens here in the CO2, plus now I have 3 here from the water. That gives me 7 oxygens on the right. So now notice my carbons are balanced, my hydrogens are balanced. All I need to do is put a coefficient here to change the oxygens. Now you might be thinking, but wait, no matter what number I put here, I have to multiply it by 2, and there's no way I can get 7 then. Well, here's where the next trick comes in, or the next hint. When it's helpful, think about or use fractions to balance the equation first. Now we're not going to leave it as a fraction, but think about this. What number, even if it's a fraction, would I put in here? So what number times 2 equals 7? Well, the answer is 3.5. If I had 3.5, or 3.5 molecules of oxygen, 3.5 times 2, that would give me 7 oxygen atoms. So notice that equation is balanced. 2 carbons on each side, 6 hydrogens, 7 oxygens. Now the problem is we can't actually have half a molecule. So think about this in terms of relating this to empirical formulas. This, in a way, it's very similar. We have our ratio. We have 1 to 3.5 to 2 to 3. To make them whole numbers, because they ultimately have to be whole numbers, we multiply them all by a coefficient. Well, if I multiply them all by 2, that will keep the same ratio, but it will make them all whole numbers. So if I go through to get rid of my fractions by multiplying them all by the same thing, I'm going to multiply them all by 2, that will give me my final balanced equation. The one that students forget is this first one here. Because we don't put the 1 there, a lot of times we forget, but remember, if there's nothing there, it's understood to be 1. So 1 times 2 is 2, and then 3.5 times 2 is 7, and then 2 times 2 is 4, and then 3 times 2 is 6. So the final balancing here goes 2, 7, 4, 6, and it is balanced. All right, a couple more examples. This one looks pretty straightforward. Fe and Cl, just doing our counts. 1 iron on each side. Again, remember that 3 only applies to the chlorine because there are no parentheses. And I have 2 chlorines on the left and 3 on the right. Here the hint or the trick is to think about least common multiple. Because for my chlorines, regardless of what number I put here, I have to multiply it by 2. Regardless of what coefficient I put here, I have to multiply it by 3. So my number of chlorine atoms has to be some multiple of 2 and 3. So think least common multiple. Well, the least common multiple of 2 and 3 is 6. So to get 6 chlorines on the left side, I need 3 Cl2s, because 3 times 2 is 6. And on the right side, I would need 2 molecules of the FeCl3, because 2 times 3 is 6. Now notice when I put that 2 there, though, it does change the ions to 2 on the right side. So I will need a 2 coefficient here on the left side to give me my 2 irons on each side. So now it's balanced, 2, 3, 2. All right, and one more example here. Again, this looks a lot more complex with this very long formula here, but this is really not too bad. So here's an example where I see a polyatomic ion, the NH4, the ammonium ion, and actually Cr2O7 is also a polyatomic ion. It's a dichromate ion. But notice those 2 ions do not appear over here on the product side. So I just have to balance each of these individually. So doing my counts here, I have 2 nitrogens. Is that 2 there because it's outside the parentheses applies to the nitrogen, which is inside. I have 2 nitrogens on the right, so that's balanced, at least to start with. I have 8 hydrogens on the left because 2 times 4 is 8. Again, it's not 2 plus 4, 2 times 4. So that's 8 hydrogens on the left. Then I have 2 on the right there in the water. I have 2 chromiums on the left right here. I have 2 chromiums on the right here. I have 7 oxygens on the left right here. And on the right, I have 4 oxygens, because notice I have 1 here plus the 3 here, that makes 4. Here the hint is this. If possible, only add coefficients where necessary. Or another thing to think of is think in terms of particles or molecules. Here's what I mean by that. Notice I need 6 more hydrogens, because I have 8 on the left and 2 on the right. So I need 6 more hydrogens, and I need 3 more oxygens, because I have 7 on the left and 4 on the right. So 6 more hydrogens, 3 more oxygens. So that's twice as many hydrogens as oxygens. Well, notice we have this water molecule here, which has 2 hydrogens and 1 oxygen. So think, how many more water molecules would I need if I needed 6 more hydrogens and 3 more oxygens? Well, the answer is 3 more water molecules, because every one of them has 2 hydrogens and 1 oxygen. So I need 3 more. So a common mistake students will make here is they'll put a 3 in here in front of the water. The thing is, though, if I put a 3 there, I actually only have 2 more than what I started with. Because remember, right now, even though we're not seeing it, there's a 1 coefficient in front of every one of these. So if I want 3 more, I need to put a 4 here, because that now gives me 3 more water molecules than what I started with. So if I do my counts now, I now have 8 hydrogens on the left, all 8 of them right there, and I now have 7 oxygens, because I have 4 here plus the 3 here. So that equation is balanced. All right, so looking at our learning goal and success criteria, we looked here at explaining what it means to balance an equation and why it must be done. And we also looked at how we can balance chemical equations. And again, the thing here, ladies and gentlemen, it just takes a lot of practice. You have all sorts of practice that you'll be able to do on the worksheet and some practice stuff. After a while, you guys will be very adept at doing this. At first, it might be a bit frustrating when you're not seeing all the patterns and you're not real comfortable with all the hints and the tricks. But a little bit of practice and followed by a little more practice, and you will have it down, no problems.